In this video, we will discuss about atomic absorption spectroscopy or AAS. Where do we use AAS? AAS is used to find the concentration of elements in a sample or to find which element is present in a sample. Basically, AAS is used for the determination of metallic elements in food industry, determination of calcium, magnesium, potassium in serum, determination of lead in petrol, etc. etc. Ultimately, it is identifying the element present in the sample, also the concentration of that element in the sample. That is quantitative and qualitative analysis of elements. Now let's see the instrumentation part. First important component is the radiation source. Radiation sources of different types. Usually used ones are the hollow cathode lamps and electrodeless discharge lamps. Mostly hollow cathode lamps are used. Electrode discharge lamps are used for analysis of volatile elements like arsenic, antimony, bismuth, cadmium, mercury, etc. Now, in hollow cathode lamp, it is a tube-like structure which is filled with inert gas such as argon or neon. It consists of cathode and anode. Cathode is made up of metal of interest. That is, if we are analyzing sodium in a sample, the cathode of the hollow cathode lamp will be made of sodium. If we are analyzing potassium, we choose hollow cathode lamp with potassium as cathode. That is, cathode of the hollow cathode lamp will be of the element which we are analyzing. And there is anode, also inert gas is filled in the tube. When current, that is high voltage, is applied between anode and cathode, the inert gas filled inside gets ionized. The ionized atoms hit the cathode. When it hits the atoms of the element, for example, if we are analyzing sodium, the cathode is sodium. When inert gas hit the sodium cathode, atoms of sodium releases in the tube and forms a cloud of atom. This process is called sputtering. Some atoms so released will be in high energy state. High energy state is very unstable. So to become stable, it releases some energy to go back to the ground state or low energy state. Here, this extra energy is released, but every atom can emit or absorb energy only of specific wavelength. Likewise, for example, sodium can absorb or emit radiation of 589 nanometer wavelength only. So suppose if sodium atom cloud is formed inside the tube, sodium atoms to go from high energy state to low energy state or ground state release 589 nanometer wavelength energy radiation. So this wavelength of energy passes out of the hollow cathode lamp. That is, from a sodium hollow cathode lamp, 589 nanometer wavelength energy radiation passes out. And this falls on our sample. This is the first part of the instrument. Now let's see the second part of the instrument. This is where we insert our sample. This happens simultaneously, that is, from one side radiation from the lamp is passing while from the other side sample is injected. Hence, radiation is reaching the sample continuously. So now we will see how the sample insertion occurs. The sample solution is first passed through the nebulizer. Nebulizer converts this sample solution into tiny droplets or aerosols. These droplets mixes with the oxidatives and fuels. That is, here in flame ionization, to maintain the flame, oxidative and fuel components are required. Here we use air using vacuum pump as oxidative and acetylene gas as fuel to burn the flame. So now our tiny droplets of sample from the nebulizer mixes with the oxidatives and fuel and reaches the atomizer. From the name itself we can understand atomizer is used to form the sample into atoms. Atomizers are of different types: flame atomizers, furnace atomizers. In flame, as the name indicates, there is flame. Here atomization occurs in different steps. Firstly, our sample, which is dissolved in the solvent, reaches the atomizer or flame. The solvent gets evaporated. The sample remains, and this gets converted into gaseous molecule. This is called volatilization. In AAS, sample, whether given in liquid form or solid form, is eventually converted into gaseous molecule. Now this molecules dissociates and produce atoms. This is what happens in the atomizers. In the furnace atomizer, instead of flame, there is graphite rod which is kept at uniform high temperature. Here, the solvent gets evaporated. As the temperature is high, the solvent gets evaporated and the sample is converted into atoms. Now, this atom interacts with the energy emitted from the hollow cathode lamp. That is, considering the example of the sodium, hollow cathode lamp emits wavelength of 589 nanometer. This falls on the atoms produced from the sample in the atomizer. In the sample atoms, if sodium atoms are present, it absorbs this radiation and reaches the high energy state or excitation state. If concentration of sodium atom is more in the sample, it absorbs more radiation. If less concentration is present, the absorbance will be less. So, as much amount of sodium present in the sample absorbs that much radiation from the hollow cathode lamp source, and the rest of the radiation is transmitted. This transmitted radiation reaches the monochromator focused by the lens. Monochromator has slit, grating system and lens. The transmitted radiation passes through these. We can adjust the monochromator such that only one specific wavelength can pass through it. Here for sodium, the wavelength is set to 589 nanometer. Monochromator filters and passes only 589 nanometer wavelength to the detector. This signal from the detector is passed through the computer system. Here a graph is obtained. Here the graph obtained is of absorbance versus concentration. What we measured is transmittance, but with Beer-Lambert's law we can obtain absorbance from this transmittance. That is, absorbance is equal to log of 1 by transmittance, log 1 by T. So from transmitted light, absorbance is obtained. Now to analyze the concentration of the element, say for sodium in the sample, first we need to calibrate the instrument with the known sample or the standard of sodium. A calibration curve is thus formed with the non-standards of different concentration. That is, standards whose concentration is known to us is diluted to different concentration and a standard curve is formed. Thus, after forming the concentration curve, when an unknown sample is analyzed, say for example, an acid digested milk powder sample is prepared by adding 250 mg of sample plus 4 ml HNO3 plus 4 ml diluted 2% HNO3, that is acidified water. We prepare a sample, a digested sample from this, and this is an unknown sample with unknown concentration of sodium. In unknown samples, concentration will not be known, but we can obtain the absorbance reading from the AAS. Here, to know the concentration, say the sodium concentration in the sample, after following the same procedure, the absorbance obtained is compared with the calibration curve obtained from the non-standards. By matching the absorbance with the standard curves, concentration of the element of the unknown sample is thus identified. Thus, using the atomic absorption spectroscopy, we can successfully identify and quantify, that is to obtain the concentration of any elements present in the sample.